Clicker's out. All those in favor, 1, A. All those opposed, B. Whatever it is. You got a question? Now, I found out this morning that I made a mistake with the quiz. So we cannot undo this at this point. But how's this supposed to go? B, record the vote. I had no final exam in this class because I thought, oh, you guys have so many final exams, let's make it easy for you and have the final exam as a quiz in class. And that was meant to be a kind favor to you. What I found out, at least from one person in the class, is that some of you have very few final exams and tons to do this week. So it worked out backwards. So all who would have preferred that instead of having a final quiz, we had a real final exam, vote A. And all those who prefer the quiz, vote B. Okay. A real final exam, the quiz final exam. Okay, so I did a little better, but it's still not the friendly system I want. Just out of curiosity, anybody have if my whole goal was to make a friendly system, anybody have a suggestion for how to make it more friendly? What? No quiz, and just base the grade on everything else? Yes. Okay, just out of curiosity, I'm not saying that I would consider this now or in the future, but A, no quiz or final exam, and B, you like a quiz or final exam. Now that's interesting. Okay, just so you know, my personal opinion is the most fair grading system is to have approximately a 2-hour final exam, give people 8 hours to do it, so it's absolutely not time pressured, and base the entire course grade on nothing but the final exam. In other words, it should be that a course is about what you know at the end of it, not how much you kept up with the homework and stuff like that. And you want to grade what people's final knowledge. But we don't have the time for that system, and so I've never implemented that. But that's the one I would like the best. Okay. Let me just get something else out of the way. Various of you are worried about grades. You got into Cornell in part by having good grades, and presumably part of how you got good grades was being worried about them, so you're stuck with that. As you know, I think by now, is I don't like dealing with the grading system. There are two extremes which I would like better than the current grading system. One is just recording class rank, and the other is just making every course pass, fail, not even pass, fail, but pass, and if it doesn't pass, it's not on your record. At Cornell, we don't have either of these options. What I can do, though, in a class like this is I can grade soft. So my plan in this course is just to grade soft. I'm not going to give everybody A's, but I think you will have trouble if you've done all the homework, if you've attended class regularly, if you do the project, if you do a decent final report, you'll have trouble getting below a B minus. So I will try to grade this course in a gentle way so that you won't feel like you deserve better than you get. I would like to think at the end. Okay, as inspiration, I've told you you're supposed to have, I would like you to have a MacGyver-like attitude. I've tried to challenge you some in this class. Some of you have seen this video, but some of you have not, so it's one of those internet things that got passed around. This is what I would like you to have an attitude like this. So here's how it goes.
Her har du tågsinne og de tekniske tegningene. Og Martin kan begynne å bli ferdig med midget. Det er bra. Ja. Og noe batteri til monitor. Ja, det er masse ekstra batterier også. Henrik! Kjapp deg ned, vi må ut! Kjapp deg, Henrik.
Who's seen that before? A few of you. Anyway, you're supposed to have that. It's really fun to do fun things with engineering attitude. Now, another shameless promotion. Here is a robot from our lab. This is largely built by undergraduates. This robot, for a few weeks, a couple years ago, had the world's robot walking distance record. So it walked a little over 5 miles with no one touching it. Here it is. Here's a video of it, somewhat before that record. On this particular night, it went 1 kilometer, which at that time we thought might be a record. I think it maybe was not. So this has batteries in it. It's got about 2 pounds of batteries in it. It's got ankle motors and it's got hip motors. It's in the world of walking robots, it's pretty uninteresting, but for that it is energy efficient and walks far. So it's much more energy efficient than, well, I think the only walking robot I know that's more efficient than this one is another one from our lab. Unfortunately, that one is very efficient and always falls down. This one at least doesn't fall down. So this one, remember X equals X, was this Laurie Anderson song I played for you? Laurie Anderson also explains how this robot works.
You're walking, and you don't always realize it, but you're always falling. With each step, you fall forward slightly, and then catch yourself from falling. Over and over, you're falling, and then catching yourself from falling. And this is how you can be walking and falling at the same time.
Catch it, man. Okay, now you can catch it. It's a big, that Spartan Hall filled with 4 of us at 2:30 in the morning. Okay. After that, walked 5 miles. A few weeks later, a company in Boston called Boston Dynamics, which makes a robot called Big Dog, they put a bigger gas tank on their robot, and it walked 12 miles. And we're hoping this winter we put new lower power electronics and a better control system. We're hoping this winter to take back that record. Okay. Any questions about future engineers or walking robots? I got one email asking for some help, and the help that was asked for was about gears. I feel like I've confused you again and again about gears, or challenged you, or given you an opportunity for learning again and again about gears. But I think rather than repeat things I said many times, I'm going to go back and repeat something I said at the very beginning about gears. And then it maybe will help some of your conceptualization, and maybe will not. So one gear is this round thing, and it's got teeth on the edges of it. And in the middle of it, there's a bearing, which is mounted to something. So this gear can go round and round. And then at one key place, there's a force on this gear. And I'm just going to call this force F. And that's going to be the force from some other gear that's going to touch it. But we're not going to worry about that gear yet. And then there are other forces acting on this gear. And they come from a motor or from anything else or from another gear somewhere else. And I can call these F1, F2, F3, F4, F5, like that. And the key idea in mechanics, it's the main idea in mechanics, is that if we look at a free body diagram, so we replace this with some reaction forces here, but let me call this point O. If we look at the sum of the moments, this big sigma signal means sum, and we look at the sum of the moments are the same as torques relative to O, that these things add up to 0. And this is with this assumption of statics, meaning that we leave out the angular momentum of the gear. And the idea is that these forces are so big compared to what it takes to make this rotate as fast as it's rotating, that the forces, or the moments of the forces, all approximately cancel. So even though the gear is turning, you use the statics equations on the gear because the inertia term is so small. The I alpha term or the J alpha term or whatever you, J omega dot, I don't know what notation you like from your high school physics. Now, each of these forces causes some moment. So if we look at one particular force here, let's say number 2, there's some radius to, and then this force has some perpendicular component, which is this part here, which is this F2 perpendicular. So when we do this statics, it turns into F1 perpendicular times R1 plus F2 perpendicular times R2 plus all the way down to F5 perpendicular times R5, all the way down to the last term, which is the radius of this whole thing. So let me just call this R, and let me call this R of this gear 1, because I'm going to have a second gear. R of this gear 1 times this thing I'm going to call F, and that whole thing has to add to 0. So that is the equilibrium of this gear. All the torques have to add to 0. And this is what I keep saying, if you understand teeter-totters, you understand all of mechanics, in particular you can understand the gear, that just like in a teeter-totter, when you have a little force over here and a big one over here, the distance times this force plus this distance times this force, they have to balance. And they have to add to 0 if you pay attention to all the signs correctly. So what do we mean by this perpendicular? We mean the thing which causes this to rotate clockwise. So for this equation, we're going to take clockwise as the sign convention. Now all of these forces could come from a motor, they could come from a hand gripping this thing, and the net effect of them is this whole collection of things here, and that net effect, we can call that M1. So what we have is M1 plus the radius of gear 1 times the force on the next gear over is equal to 0. So what we do is we summarize the torques of all the applied forces, torque of all applied forces, and this is the net torque of all the applied forces, and that we can take to be this thing we call M1. So what does that say? It says the force acting on the next gear over is the moment applied to this gear from the motor or from the rest of the gear train divided by this radius. So let me call this, instead of 1, let me call it gear A, and let me call this RA and FA. So we can we'll use A's and B's for the two gears. Now meanwhile, there's another gear, and that other gear is the one which is touching this first gear. So this is the other gear, and we can draw the same picture for this other gear. It's got all these teeth on it, and it's got some force in the middle, and I'll call this O prime here. And then there's an action and reaction force here. So here's this force up here, which is this FA, again, only now is pointing up. And here is this radius, which is RB. And then there are all these other forces acting on this thing. And I can pick whatever sign convention I want over here. I'm going to pick a sign convention over here where clockwise is positive, like that. And so I have all these other forces acting on this, and I'll call these MB. And so we have MB plus FA times RB is equal to 0. Let's see, this is a clockwise force down, and this is if this is causing this one to turn clockwise, and so it's pushing up and causing that one to turn clockwise. So we have here that MB is equal to FA over RB with a minus sign, but this FA was M1 over RA. So we have M1 over R. Did I get that right? Sorry. This is times RB. This is F over RA times RB. And this gives an M1 times RB over RA, or MA. And then there's a sign issue. And if we want to be careful about the signs, which is tricky to do in these problems, and I have not been careful about the signs all semester long, I have here that I'm summarizing this gear A as having this clockwise moment MA, and then this force here. And with this sign convention, this moment is going to have this opposite sign from this force. So there's this minus sign goes through like this, and we have this MB is equal to this radius ratio times MA. So you turn on this gear this way, and there's an applied torque this direction. That's trying to turn this thing this way. And so there's also an applied torque in the same direction on this one. But they're rotating in opposite directions. Okay, so what you have here is the same thing that we get out of the lever, which is that the ratio of the moments is the opposite of what we get for the ratio of the angular velocities. How does that work? Is because the velocity of this point is equal to the velocity of that point. That's the Laurie Anderson song, let x equals x. But the velocity of that point is omega a times RA. It's also equal to omega b times RB. If we want to be careful about the sign conventions, about what's positive and what's negative, and we want to use the same sign convention for both, we put a minus sign there. And so we have the ratio of the angular velocities is equal to minus RB over RA. This is what I called A. This thing is called 1, it's called A. So here we have this angular velocity divided by the second angular velocity is the reciprocal of this torque divided by that torque. So if the gears make the angular velocity of B bigger, it makes the torque on B smaller, and vice versa. And this is this dual relationship you get. Now if you put 3 gears, 4 gears, 5 gears, that property persists, that when you amplify the motion, you attenuate the torque, or when you amplify the torque, you attenuate the motion. Okay, so that's the basic concept of this transmissions is that they either amplify or attenuate force or torque, and they either attenuate or amplify velocity or angular velocity. Yes? Okay, so intuitively, why the moment's in the same direction? Here we have the moment of other things, not of this force, but of other things on this gear. And here, when we look at the second gear, we have the moment of other things, not of this force on this gear. Okay. Now if we take this gear train and I try to turn this like this, I try to turn it, say, clockwise, that's going to turn this one counterclockwise. And if I'm going to keep the whole thing in equilibrium, I have to stop it. And it's going to take a clockwise torque on both of them to keep this in equilibrium. Okay, any questions about, go ahead.
I was just wondering how, when you open
Yeah, so this is supposed to have a minus here, which is how the positive came out over here. So this one came out positive. Thank you. Anything else? Okay. So the other request was about how to do guessing to solve differential equations. And the short answer is there is no how-to. There is, you guess, and you plug in, and you see if it works. And if it doesn't, you guess again, and you plug in and see if it works. That's the how-to. Does anybody want to see examples of that or not? All in favor of example of guessing to solve a differential equation? All opposed to guessing to solve a differential equation? All who are wishing that this week just passes by and the one after it too? Okay, so we have 25 minutes here, and I will talk about whatever you want me to talk about. Maximize the gear ratio.
car problem?
So maximize the gear ratio.
Yeah, we already maximized velocity.
It's hard to imagine I asked you to maximize the gear ratio.
Find the gear ratio that minimizes the time.
Find the gear ratio that minimizes the time. Aha. That's a different question. Okay, you want to maximize the gear ratio. Say on a bicycle, how do you do that? You make the front sprocket infinitely large, or you make the rear sprocket infinitely small, or you make the rear wheel infinitely large. Okay, now optimize the gear ratio I've given you several problems about optimizing the gear ratio, and all of those problems have to do with the following thing. If you have a given motor which does what it does, and you have too high a gear, which is too low a gear reduction, then a very small force comes out of it. And your car doesn't accelerate, or your bicycle. If you have too large a gear reduction, a very big force comes out if it's stalled, but then it goes faster and faster, and the motor loses its oomph, and when the motor is going full speed and can't do anything more, the car or bicycle is still going slowly. And you have had this experience in cars and bicycles. Those of you who've been on a bicycle, if you're on an 18-speed bike and you start in a very low gear, you'll start really fast because you'll have lots of force at the rear wheel with your given muscles, your given legs, but the bike won't go very fast because you spin your legs and they only spin so fast. If you start in a very high gear, 28th gear or 21st gear or 15th gear or 10th gear or 3rd gear, going back in time for the various bicycles that we've had available, and you start out, the bike accelerates slowly because you have a small force there, and then you get up to speed and everything's going good, except for now there's some wind resistance. And you don't have a lot of torque, and you can't fight the wind, and you can't go very fast, or there's a small hill. So in between, there is some optimum. So how do you go about finding that optimum? Is we say, if we put in some gear ratio, which we'll define as, say, the gear reduction, what we get out is some quantity of interest. Some maximum speed, I'll just call it Q, which is going to be different for different applications. It's going to be a maximum speed. It's going to be the speed, the maximum speed you achieve when you reach steady state. It's going to be how long it takes to get through some race. It's going to be the average speed in some race. And you want to pick the gear ratio that makes you do the best job at this performance. And in general, you'll find too low a gear is bad and too high a gear is bad. So how do you optimize the gear ratio? You make a plot of whatever this performance is. The time, say, to complete a race course. And what you find is the time to complete the race course is some function of the gear ratio. And when you optimize, you want to try and find this point here. And that's how you optimize. Now, how do you go about doing that? Well, you can draw a graph, literally, by doing this calculation. How do you do this calculation? In the problems I've been giving you, you do this calculation by solving differential equations and so on. Or, since you've got the whole thing on a computer anyway, you solve the differential equations and you keep guessing solutions in some iterative way to try to find this bottom point. Okay, does that address your question? So the conceptual thing is when you optimize, you look at the performance versus the thing you're controlling, and you find the best point by drawing a graph and finding that best point. Or looking at a list of numbers, or iterating on the computer, and so on. Totally address your question? Anybody else have a question about this question? Just so you know, trends in engineering calculation, optimization is getting to be a bigger and bigger part of engineering. And the reason is that these forward calculations, where you're given something and you can calculate the output, people are getting so good at it that they can automate this process and therefore think, what is the best thing to get the best output? So we didn't have the luxury of doing optimization in the past so much because the forward calculations were so long. Now that we're getting so good at the forward calculations, there's lots of optimization in engineering. Yes? And when I say lots, it's like a really rapidly growing thing in the past several years. For example, in the design of our robots, only in recent years have we started to actually try to formally optimize, say, the energy use. Because the forward calculation is so hard that we're just barely beginning to be able to do it well enough that we can do it enough times that we can do the sequence of guesses to figure out how to control the robot to minimize the energy. Okay, other questions? Anything. You can ask anything about any topic. In this class, out of this class, grading of this class, content of this class. What's mechanical engineering about?
Can you go over ODE solver?
In MATLAB?
The syntax.
The syntax. Do you want me to do it on the board or on my computer?
Board would be nice. Actually,
How many people in favor of this syntax of ODE solution? Okay, we started out with just one variable, and let me just go back to one variable again. And the basic concept is we're going to have two things going on. One is we want to describe what is the ordinary differential equation. And the way I've tried to describe ordinary differential equations to you, they are crystal balls. They are rules that if you're told the current state of a system, what do we mean by the current state? We mean all the numbers which describe the system. it tells you the rate of change of those. And the crystal ball, those rules, usually are, say, Newton's laws or some physical laws. But let me give you a different example. In fact, I'll just do this example and make it two variables, which is let's look at x and y. In fact, I'm going to give it more suggestive names as P and S. I used to have housemates named Phil and Sally, and they had this ongoing relationship, which was worked like this. The current state of the system is how much Phil is in love with Sally, and how much Sally is in love with Phil. So there's going to be these two numbers, which is how much they're in love with each other. And the way it worked out is when Phil was nice to Sally, that increased her affection to Phil. She had a regular, healthy personality that when he was nice to her, that made her increase her affection towards him. And he had this personality that the nicer she was to him, the more he thought, any club that will take me as a member isn't one that I want to be a member of. And the nicer she was to him, that decreased his affection towards her. Okay, so we think of this as being Z. This collection of things is Z. And this whole collection of things is the rate of change of Z. So we have that we can calculate the rate of change of the state from the current state by these two numbers. Okay, these are the rules, and these are the dynamics of their relationship. So how do we put this into the computer is we've got to say, I've got this rule which is going to describe the differential equations, and it's going to tell me the rate of change of the system. This word here can be whatever I want it to be, but it has to be that in the end of this program, or this function, I tell the thing which is going to solve the differential equation the output. So what is the output? It's got to be, this function has to have a name. I usually call it something like my right-hand side. This stuff over here is what we call the right-hand side. This is my right-hand side, my description of my friends Phil and Sally. And what we say, if we know the time of day and we know the current value of the state, we're going to spit out the rate of change of the state. So this has to have in it this differential equation. The differential equation is that P dot is equal to minus S, and S dot is equal to P. But this has in it only Z and Z dot. So I've got to say what's the output. It's going to be these two numbers, P dot and S dot. The MATLAB happens to want this as a column vector. And then I've got to say what's S and P. So I'll say S is equal to Z1 and P is equal to Z2. And I'll put semicolons everywhere so that MATLAB doesn't spit out a complicated list of numbers. So here's how to describe the differential equation to MATLAB. This whole thing is MATLAB's way of saying this whole thing. Okay, any questions about that? Yes?
Will it matter that S is Z1, but P dot comes first?
No. Because it knows what S is, it knows what P is. This is just calculated two numbers. There's no dependency here. So you just go through this in order. You calculate this, you calculate this, you calculate this, you calculate this. And if I put them in a different order, the result when I got down to here would be the same. If on the right-hand side here there had been a P dot or an S dot, we'd be in trouble. But the way we think of differential equations is as these crystal balls where you take it the rate of change only depends on the present value. And in this case, it's not Newton. What have we used so far? We've used Newton's laws, plus this geometric law that velocity is the derivative of position. And now we're using the laws of psychology. personal dynamics, but it's still a crystal ball that lets you predict the future. And using this, we can figure out how Phil and Sally's relationship works. So we could, if we solve the differential equation, we can look at the solution. The solution says let's take some initial state. The initial state is that Phil noticed that Sally was kind of cute, and Sally, say, didn't notice Phil at all. And so we have this initial state, which is P0 is equal to 1, say, and S0 is equal to 0. And we can try to look at what these functions of time are that will be the solution of the differential equation. Anybody know what those functions of time are? Anybody know anybody who's been in a relationship like this? Most of you do, I think. How does it work? Phil starts out liking Sally. She doesn't notice him. So he gets more and more friendly. That makes her more and more friendly. He doesn't like that. He gets less and less friendly. Eventually he's not friendly at all. She doesn't like that. She gets less friendly. She's got a negative S here. He thinks she must be pretty good. He chases after her. He gets more friendly, and so on. And so what comes out of that is he starts interested. Her interest starts to grow. That makes his interest wane. Her interest is still growing because he's still got a positive interest till he has no interest at all anymore. Therefore, her interest is at a maximum. He gets less interested. Her interest starts to decline. He doesn't decrease his interest at such a big rate anymore until her interest gets to 0, at which point he keeps his interest constant, but negative. She doesn't like that. She likes him less. He says, hey, that's starting to look good. And so it goes. And you can make a cross plot of this, which is a plot showing P and S. So we plot P versus S. This would come from the MATLAB command of plot on the x-axis P, on the y-axis S. Over here, this would come from the MATLAB command plot T, P. This would come from plotting T, S. And the cross plot starts here, and they go round and round like this. And after some months of this relationship, she would naturally say, hey, we're just going round and round in circles. Let's get out of this thing, right? Okay, so how do we tell MATLAB to solve these differential equations? We say, I would like to know at a long sequence of times the values of both Phil and Sally's emotions, and so we're going to take and have the whole solution laid out as a big matrix, a matrix of time and a matrix of the Phil's values and Sally's values. So the output is going to be this 3-column matrix, and this is the time 1, time 2, time 3, and all the way down to the last time. And then next to it, we're going to put this 2-column matrix, and this 2-column matrix is going to be Phil's feelings and Sally's feelings at time 1, Phil's feelings at time 2, Sally's feelings at time 2, and so on. And this matrix we're going to call Z array, and this matrix we're going to call T. And so we have to get that out. How are we going to get it out? We're going to say we're going to use MATLAB's differential equation solver. What is this? This is a fancy version of the program which you wrote yourself, which is this thing which moves forward in time. Takes the current value, looks at the rate, goes forward 1 step in time, because you know the rate of change, just like I drew on the blackboard here. You use the rules for predicting the future to increment forward in time. And here is a program that does it. It does it a little bit smarter, just like the trapezoid rule is a little bit smarter than the left rectangle or the right rectangle rule, and Simpson's rule is a little smarter than that, and this is even a little smarter than Simpson's rule, but it's basically a way of marching forward in time, predicting the future based on the present, going forward in time. Now, if MATLAB is going to solve these differential equations, it's got to know where are the differential equations. So one thing you have to tell it is the name of the function that holds the differential equations, which is my right-hand side. And for some reason, you have to put the @ symbol here. You have to tell it what's the time interval you're going to solve it in, and you have to tell it the initial conditions. So that's the syntax. That means somewhere up here we have to put what is the time interval, and we can put here, say, 0 to 10. And we have to put in here what is the initial condition, and in this case I put that it was 0 and 1, 1 and 0, which were the initial values of Phil and Sally's feelings. And in this case, it doesn't care whether it's a row or a column. And it's a little bit confusing here, because when it does z dot, it wants to, for some reason, the MATLAB wants to treat the syntax of the ordinary differential equation solver wants this as a column, but at each instant in time, it spits it out as a row of this matrix. Yes?
When you type, when you're writing the 1, 0, does that have to match S and P at the bottom? So whatever, so whichever one's C1, so this is going on.
So this is P0 and this is S0. These are the values of P and S at time equals 0.
And it's the bottom, you said, does it have anything to do with Z1 and Z2 and how you said S equals Z1 and Z2?
It does. I could put above this line, if I wanted to be extra clear, I could have put here P0, S0, and before this line I could have put P0 is equal to 1, S0 is equal to 0, and then that would make it especially clear that these two numbers are corresponding to these P and S.
Aren't you going to, isn't it going to contradict this with S and P? Is going to come to the wrong matrix?
You mean, didn't I do this wrong? Is that what you want? I've been calling P Z1. I did this line backwards. Is that what you're trying to tell me? Yes. I had this line backwards. I've been using the first variable for P and the second one for Sally. Phil is first, Sally second. And then to unpack this array, I can put P is equal to Z, and I'm going to take all of the first column of Z to be P, and I'll take S to be all of the second column. And then these plotting commands will work over there. And then I have to also put an end to this first half of this program. So this is the ODE, and this is solving the ODE. And just to complete the story, Phil and Sally are real people, and I taught differential equations, Math 293, some years ago when they both lived in town. And on the last day of classes, I did my last Phil and Sally example. As the semester went on, I included more subtle terms in these dynamics. Then I had Sally come to the last class, and she stood up at the very end and turned to the class and said, "I'm Sally, and it's all true." Okay. What? Who was Phil? Phil Bogdanoff. He lives in Washington, D.C. Nice guy, but for his ways of dealing with Sally. No, far from it. She's in Berkeley, California. He's in Washington, D.C. They're each married to other people that have better dynamics. What? Phil sounds someone who didn't like him but would stick around. I think Phil changed, actually. I think Phil grew up. Okay. Questions? We got 4 minutes left. More about Phil and Sally? Yeah?
If you want to pass parameters on the right-hand side, how do you do that?
Okay, if we want to pass parameters, so one of the things that I've been hoping you've been learning is how to suffer through the incredibly complicated help responses you get to help commands in MATLAB. And the reason you get incredibly complicated responses to help commands in MATLAB is because people want to do all kinds of things. And for example, this command ODE23, there's lots of things you can control about it. And this is the minimal way of using that program. But a way to use it a little bit more, with a little bit more sophistication, is to say, okay, there's all kinds of fancy stuff you could do. I don't want to do that, but I do want to pass in some parameters. And you put that syntax like so. And then this program ODE23 will pass in these parameters, and it will pass them all the way down to here. So you put in these parameters, and then up here I have to go to the parameters, and I can put in here a list of numbers, 17 and 36. And then in here I could put param 1 is equal to params. Let me just call it C1 to make it shorter. For C1 is equal to params 1. C2 is equal to params 2. And I can put in other things here. For example, I could put in C1 times S, C2 times P. And then I would have a different dynamics. Who asked the question? Who asked the question about parameters? Does that answer your question?
Yeah. Is param global or is it local?
It's completely local. So this is good programming style, which is to only pass, as those of you who take CS100 or programming class, they advertise against what are called global variables. Global variables are ones that if you have other programs running, they can all see them. This only passes the information. So params is local to this program. It gets passed into OD23, and then that gets passed into here. Any other programs around do not see that value of params. There's another way of passing the parameters, which is to use a global statement, which I can show you if you want. What? I could put a statement here, global D, and I could put down here a corresponding statement, global D, and then I can put D equals 16, and then I can put here plus D, and then that passes also the value of D into this program. That's actually a little easier conceptually, but it's considered bad programming practice.
Wait, you have to differentiate these.
You have to have the global statement in both places, so it's only so global. They both have to agree that it's global. Now hidden in here, there's a whole bunch of stuff you can put. Has anybody gotten into this world of options in ODE23? Did anybody try options? So there's something that I've had you do for sure the hard way, because I didn't want to get into this complicated syntax, which is in solving for these car problems, when we solve the differential equations, we have t as an independent variable, and we look at how far the car goes or the bike goes as a function of time, and we're interested in how long it takes to get to the goal line, but we can only put in what the time is that we're going to integrate for, and what you find out is that you went too far or too short, and I've showed you this method of sequential guessing to try to get the exact time it takes to get to the goal line by solving the differential equation again and again, or using root finding, or drawing the graph, or something like that. In fact, there's an option that you can use in the differential equation that says stop solving when one of the variables gets to some value. Much simpler. I just didn't show it to you. Now, why didn't I show it to you? It's because I'm not trying to show you the most efficient way to solve one particular problem in MATLAB. I want you to think about being able to solve roots and hack your way through it. But the options could save you lots of programming effort in that case. The only way to teach is by lying. So Thursday we have this exam. What? Say again? Final exam. Quiz 2. My intention is to make it lots of short questions. No, I do not intend there to be any long calculations. Though I just because they're short calculations, I don't expect all of you to be able to do all of them. I expect at least some of you. Any given question, I hope at least one person gets right. So they're all going to be inbounds in terms of things which you could have learned had you been on top of things. Most of the questions should be more inbounds than that most of you should get them right. It's a mixture of easy and hard questions, right? I don't want you to get everything right. Yeah?
Are you required to know like all the formulas you gave us?
Are you required to know X? And the answer is you are not required to do anything. If you want to get every question right on the quiz, you will know absolutely everything that was in absolutely every part of this course and any natural things you would have learned in trying to understand those as well. So this is not a class where I have a list of 100 facts. I just want you to master it. I want you to have been thinking and getting involved. Okay.